For a few decades, the automotive industry has been steadily replacing mechanical systems, mechanical components, with electronic systems, with software, with networks. I would say at least since the 80s and certainly since the 90s. That was when, for a start, the state of California introduced new rules regarding every car to have systems that would be able to detect if there are any problems with its emissions, and similar rules in the European Union in the 90s. So since at least then, the automotive industry has moved away from this state of having this messy layouts with cables everywhere, directly connecting the different components, and more towards this state where the car has a network inside, or a number of networks, a small number of networks inside it, and every different system is connecting to each other through these networks. So there is not anymore a direct connection from, let's say, this component to this component, so there's not anymore anything like this, but instead what we have is that we have a network. So if something needs to communicate between these two, then they do this, and they set information over that network. Now, why is that important? Because if another embedded system there, if another system inside that car needs information from that sensor, well, maybe it can go to that one too, and to maybe that one too. So we have one network, or a small number of networks, and all the different systems can connect on these networks. Now, beyond being very nice and tidy, beyond being very efficient in terms of the design, very efficient in terms of the use of the different systems, of the different sensor data, for example, it also reduces massively weight. And weight is perhaps the most important, certainly one of the most important parameters of a vehicle. If the weight is reduced, then that improves energy efficiency. And it is obvious that energy efficiency is very important nowadays, especially if you see any kind of commercial involving cars. It will first mention its miles per gallon and then anything else, certainly not its speed anymore. So energy efficiency is very important, and you can achieve energy efficiency by reducing weight. You can reduce weight by removing by having fewer cables, by having fewer mechanical systems, and having a network or a set of networks, and the different components connecting to that set of networks. There are a number of different functionalities in any modern car. They are usually classified in 5 categories. The first one we see here is feedback control. So the feedback control systems, one of them would be cruise control or dynamic cruise control. In cruise control, what happens is that the sensor would measure speed. So the data from the embedded system that is controlling the sensor that is measuring the speed will be sent to a computer that is controlling the cruise control, where the cruise control sits. And that data would help the cruise control system to determine whether it will increase or reduce, so how it will vary the rate of fuel in the engine, because this is what is changing effectively the speed of the car, the speed of the vehicle. So we have a set point, which is set by the driver, which is the target speed, and then we have the sensor values that are coming from the different sensors related to the speed of the car, and the actuation will be the rate of fuel in the engine. So this is a feedback control system because there is this kind of feedback from the sensors. Then there will be the discrete control systems. The discrete control systems will be something like turning the lights on or off. So if something is on or off, that would be a discrete control system. And changing the setting of the windscreen wipers would again be a discrete control system, because there is this discrete set of different settings that we can choose. There are another group of functionality is diagnostics. In fact, diagnostics is what started all of it. I must say, all of this moved towards more electronic systems. As I mentioned, it is the regulations regarding diagnostics for the emissions that, to a large extent, accelerated this move towards software, towards electronic components, and towards networks. And diagnostics, what they do is that they would detect faults in the components and record these faults, which is very important for checking, for repairing cars. And it also involves reconfiguring, updating software. There is also infotainment, so this would be at least a music player. For some higher-end cars, it might be a TV screen for the rear seats. And telematics. Now, telematics is mainly about satellite navigation, is mainly about being able to tell where a vehicle is based on its GPS position, based on GPS location. So this can be used for managing a company fleet. And this all was accelerated massively. This all became a massive industry when in 2000, just after 2000, the GPS, civilian GPS became available to everyone. In fact, to some extent, the GPS is considered a utility. In fact, the only one of the very few free utilities for everyone in the world. The type of embedded system that we have in a vehicle, we call it an electronic control unit, an ECU. Now, the term ECU is very often used also for engine control unit. Now, to avoid any kind of confusion here, I will use the term ECU for electronic control unit and the term ECM for engine control module, which would be one of these electronic control units. So there are many electronic control units inside the vehicle. It would not be surprising to see over 90 ECUs in some higher end vehicles. Certainly most cars will have at least 15 ECUs, at least 15 of these computers, of these embedded systems that are controlling different actuators, different functions inside the vehicle, inside the car. The specific one, which is obviously the most important, the engine control module, the ECM, this one takes data, sensor data, from, for example, the position of the throttle, the water temperature, the amount of air that is sucked into the engine, the level of oxygen in the exhaust. All of these pieces of information are very important for the engine control module to know how to adjust the fuel mixture or the ignition timing. So the actuation would be the fuel mixture and the ignition timing and a few more. An important point here is that ECU software, ECM software of course also, but generally ECU software, so the software that helps run a modern car, is extremely complex. It will have perhaps even 100 million lines of code. So it can go wrong. Things can go wrong in any kind of software if there are so many lines of code, of course. And to put things in perspective, that might be more than the lines of code that would be in the software of many of the current modern fighters, many kind of the modern fighter aircraft. So everyone's car might have more millions of lines of code than a whole aircraft, a whole fighter aircraft, in fact. So this ECU software can be modified. It is software after all. It is firmware, to be more accurate perhaps. And this software can be modified is often modified by the tuning community. So you often hear about engine remaps. So this is part of modifying the ECU software. Here I have a simplified version of what distributed control looks like in a car. So if we have a number of different ECUs, I'll only have 4 here, and then the actuation for one of these, let's say the actuation for ECU 3, depends on the sensor value that is collected in ECU 1. Then the information from ECU 1 is transmitted over this network. Now, in the typical case, it is transmitted over the whole of the network. So everyone will receive this information. Everyone will receive the information about, in this case, the voltage that this sensor is measuring. And this information, though, it will be acted upon by the actuator that is interested in it, which is ECU3, because it has a rule. Let's say it says switch on a light, switch on an actuator, which is switch on a light, if informed to do so by ECU1. So there will be this kind of communication between them that will happen through this network. The in-vehicle network technology classes have been provided by the Society for Automotive Engineers, by SAE, and there are 4 of them. The first one is Class A. So a network that belongs to class A will be a low rate. That will also mean low cost to a large extent, and it will be designed for non-critical functions. So a non-critical function would be, for example, to operate the indicators. So this is not a critical function. No one will die if the indicators are not in the right position or if they don't operate. So this is a non-critical function, and for this it uses the low rate network, so one that belonging to class A. One belonging to class B would be medium data rate. Again, it would be for non-critical functions. And then there is class C and class D with increasing data rates, increasing importance. So class C is where we have the critical functions, at least in class C, and they tend to have very high data rates. Class D has also very high data rates, but that may be for other reasons too. So it might be for the control of hard real-time systems, so this would be for critical function, but it might also be in order to be able to stream multimedia, because that would require many megabytes per second, many megabits per second, so that would require greater data rate. And if we are to see now some of the typical ones that belong to the various classes, the lean and low speed CAN would typically be used for low criticality applications. So that's why they have significantly lower kilobits per second speed than the ones that are designed for more critical applications. Out of these, so I will go through them actually. Lean and low speed CAN, this might be used for the windshield wipers, for the interior light, for the seat position, for mirror adjusters, door locks, and many other non-critical applications. The high-speed CAN and FlexRay, more recently, will be used for more critical applications, more safety-critical applications, I must say. For example, for ABS, for engine control, for the suspension. And then there is MOST, which is used for infotainment, for digital radio. There is Bluetooth, which is used for connecting externally, typically, devices, external devices to the car, perhaps for connecting one's smartphone or one's music player. And there is also RFID that tends to be used for the immobilizer of the car. There is also X-by-wire technology. When we talk about X-by-wire, it means that there is now, rather than a mechanical or hydraulic system connecting or operating a specific subsystem of the car, now there will be wires. There will be a network doing this. So this can be used for steering. Then we have, which we would call steering by wire. It can be used for shifting, for braking, throttle control. So all of these X-by-wire systems have replaced these hydraulic or mechanical systems with networks. So when one is turning the wheel, as in this case, then when that happens, when the wheel is turning, then this is moving these systems, and it does so directly. So the wheels will be operated according to how the steering wheel is turned. But this is physical, because they are mechanically connected or hydraulically operated. When we have a FlexRay system or any kind of X-by-wire system, I mentioned FlexRay because it is common to use FlexRay in this system. When there is any kind of X-by-wire system, as we would see in higher-end cars, in Formula 1, in racing, then there is no direct mechanical connection. So if you see here, for example, there is no connection. There's an air gap there. What happens is that the user is operating the steering wheel. It's almost like playing a computer game. It's almost like using a gamepad or a steering wheel in a computer game. And this is generating information. It's generating commands. They are sensed. Actually, it's generating data as they are sensed in here. And that data are sent through the communication network to an engine, to an ECU, to an embedded system that is controlling the actuation. So we never had the direct connection between the direct physical connection between the steering wheel and the front wheels. Instead, we had this network. We had a network packet, effectively a network message being sent between the steering wheel and the actuation and the front wheels. Important of the standards, of the networking standards that I mentioned before, is CAN bus. This is by far the most important because it is implemented in the vast majority of cars and the vast majority of vehicles. It started in 1983, so first by Bosch, joined by Intel a bit later, was presented a few years later. And in 1990, there was already the first car that was implementing CAN bus. It was a Mercedes S-Class. By 1993, it was an ISO standard. At the moment, or since then, the vast majority of vehicles are using CAN bus. In fact, since 2008, all EU vehicles in the United States require to have CAN bus for at least for the onboard diagnostics. CAN bus is a very simple protocol. It has no source. It shows no destination inside the message. Every message is broadcast to everyone that is connected to the same network, to the same bus. And only one of the systems, only one of the computers connected to this network can transmit at any one time. If there are more, then some of them, apart from one, will have to halt, will have to stop. In ISO 11898, it is described how CAN should be implemented. So this includes precautionary measures to limit the impact of a failure. Now, in practice, that doesn't mean that everyone is following these precautions, or everyone has these precautionary measures, or that everyone is implementing CAN bus in the same way, although it is a standard, of course. To start the discussion on mainly on the cyber-physical security incidents, or different types of concerns that might exist for a vehicle, and a vehicle specifically having CAN bus, but not only with CAN bus, it's just an example here. I show here a simplified diagram. So this is simplified because first of all, it's very small. It doesn't have the number of ECUs that one would expect in a network, in a car. As I said, a vehicle might have between 15 and 90, perhaps even more ECUs there. Here I have only a few, only 7 or 8. And I have only the CAN bus networks, not any of the other networks that might be connected to the CAN. And this is the powertrain control CAN and the body control CAN. Now, to simplify things, let's call the body control CAN as the low-speed CAN bus. So this is the low-speed CAN bus. It is the one that is for the low criticality kinds of functions. So, for example, the tail lights, the doors, the instruments cluster, the headlights, all of these, they are not as safety critical, one would say, as braking, of course. So for this reason, these are on the low-speed CAN bus, on the body control CAN bus. And there is the powertrain control CAN bus. Let's call this the high-speed CAN bus. And this is the CAN bus for the high criticality functions, for example, for ABS, for engine control, for suspension control. All of these will be connected to the high-speed CAN bus, to the high criticality CAN bus. However, there are many cases where a piece of a system, a piece of information perhaps, needs to be sent between a system on the one side to a system on the other side. Let's say that for a start, the tail lights need to operate every time the car brakes. Well, then there needs to be some kind of connection between, either direct or indirect, between the ABS, the braking systems, and the tail lights. So there needs to be some kind of connection between them. So that happens by having gateways. All of these, so there are, for example, the tail lights, the doors, the instrument cluster, the headlights, the engine control, the suspension control, the ABS, all of these are ECUs. There are different types of ECUs. The gateway is one more of them. In fact, it might have a different function too, but one of the functions that it has is that it serves as the gateway, as the way to connect the two networks. So this does not mean that it's a type of ECU that does nothing else. It might do other things too, but one of the things it will do, it will be to act as a link between the different networks. In fact, in one of the most impressive, in fact, types of experiments showing how to hack, how to breach the security of a vehicle through the CAN bus, what the research team from the University of Washington and the University of California, San Diego did, is that they exploited that gateway. Now, in the specific car, and this is not uncommon, the gateway was the ECU responsible for the multimedia interface, for the music, for example, the music player of the vehicle. So this was the MMI, multimedia interface, and it was also the gateway of the vehicle. So what that team did was, after a lot of research, of course, it took them 2 years to achieve these very impressive results. They created malware that was inside a music file, and that would, when that music file was played, or that when that music file was inserted somehow in the multimedia interface. So, for example, think of an SD card with an MP3, perhaps a WMA. It was actually audio file where that is infected, being inserted in the multimedia interface of the car, and that in exploiting weaknesses in the software of that multimedia interface, which, however, was also the gateway. So in that way, exploiting the gateway, and by exploiting the gateway, gradually getting control of the whole of the car, of the different types of actuation, the different types of sensing inside the car. So this was possible because there needed to be some kind of control, some kind of connection between the different types of networks. This is something that we see also in industrial control systems. So an industrial control system, you might think of the low-speed CAN bus being equivalent to the corporate network, and the high-speed CAN bus being equivalent to the control network of that industrial facility. So again, there needs to be a connection between the control and the corporate network for the different for different functions. For example, if in the corporate network someone needs the data from the control network. So, and again, in the same way, there is a gateway, there's a link between them. Well, we see the same in a car. So we'll see this connection between the different networks. And the CAN bus, the standard, is often implemented as, it can be implemented in many ways, but it is often implemented as a twisted pair CAN. This is the most common, where there is a CAN high and a CAN low, the two different types, two different signals on the two different wires. So it's a twisted pair. You see how they are twisted there. So this is twisting around here. And why is this twisted pair approach important? Why is it useful? Well, it is useful when there is noise. It is useful in situations where there is noise. Well, let's see why. Let's say that we have a single wire, and on this signal wire there is a single signal. So this signal will be the green one there. So this is voltage, and this is, let's call this the high voltage and the low voltage. The high voltage, I don't know, maybe it's 5 volts, and the low voltage might be 0 volts. And let's say that every time we see high voltage, we consider this in a digital communication context. We're talking about digital communication, so we're sending bits, we're sending zeros and ones. So let's call the high voltage a 0. Okay, and let's call the low voltage a 1. Okay, so this is by definition. We call this a 0 and a 1. And then, so that is 0 and 1. Then we have this case here, which is not quite obvious what it is. It's a spike, but it's not quite a 0, and it's certainly not a 1. So it's not high voltage, and certainly not low voltage either. That might be because it hasn't received enough voltage. So it might be intended to be a 0, a high voltage, but didn't quite make it. Or it might be low voltage, so there was nothing sent, there was no voltage there, but or there was 0 voltage there, but due to noise, due to some kind of interference, there is that spike there appearing. When you have a single signal, you cannot tell, unless you have some kind of error correction mechanism implemented and redundant bits added to the signal. It is not possible to tell whether this is a 0 or a 1. Well, the next one is obvious, that is a 1. So this is a 0 because it's high, and this is low, so it's a 1. This we don't know, and this is low, so it's a 1. By convention, we have said that this will be 0 and the other will be 1. So if we have the two signals, then we can get more information about any kind of possible ambiguous situations. So, for example, if there is any noise, if we have, so let's take the example on the right now, and again, this is voltage. And again, we have the different level of voltage. Now, the blue signal will be the signal on the one wire in a twisted pair, and the red signal will be the signal for the wire for the second wire in this twisted pair. So it's a pair. So we have two signals. At any point in time, we're sending signals on both wires. So if we want to say, for example, if we want to transmit a 1, we do the same voltage on both. So it doesn't matter what the voltage is. What matters is that it is the same. This is the only thing that matters in this case in differential signals. So this is a 1. We say that it is a 1 because they have exactly the same signal. And in this case, we call this a 0. So if there is a difference between the two different signals in terms of the voltage, then we consider this to be a 0. And again, one more 0 here. And a 1 here because it is the same. And the 0 there because there is a difference. And now notice this case. Now this is where we had the spike before perhaps because of noise. And we have indeed the spike on both. That's because the two wires are twisted together. So if there was any kind of external interference, any kind of maybe the motor, anything that inside the car is causing interference, well, this interference is expected to be similar on the two wires because they're twisted together, they're next to each other. So we don't really know the correct what voltage they were intending to be, but we certainly see that it is different. Now this is the only thing that matters. So it is different voltage, so that can only be a 0, and again the same as 0, then a 1 because it's the same voltage as 0 and a 0. So we get a whole series of bits there. We get 0, 0, 1, 0, 0, 0, 1, 0, 0, and we do that by checking the differences between the voltage on the two different signals. So this is a differential signal. Let's see the complete structure now of a CAN message. Actually, it's a CAN frame to be more accurate, but let's call it a message just for simplicity. So there is the starter frame, which is always transmitting a 0, and you can see that it is a 0 because there is a difference between the voltage between the two different signals. And then there will be 11 different bits, and these 11 bits are very important because these are the identifier. Now the identifier, not only it is an identifier, but it is also the priority. So this sets the priority of a message. If there are two messages, if there are two ECUs trying to send at the same time, and there are quite a few others. The other important one is the red one here, which is the actual data, the actual message, the actual instruction, for example, that is sent to an actuator, or the actual content, the actual values from the sensor that are sent through this message. And I mentioned that the identifier is very important, that it is the priority. In fact, the lower the identifier, the higher the priority. So a message that has a very low value in the identifier, and these green bits there, this will have the highest priority. And now that we know the structure of a CAN bus frame, well, we now know that these bits here, it was the red before, so these bits here, this 64 bits here, this is the data. So this is what we need to change if we want a different message. So this is actually what contains the instructions to the actuators. Now there is a technique, it's called fuzzing or fuzz testing. It's not really a technique, it's a kind of a very obvious approach, which is to go through all the different combinations of these zeros and the ones in this data, and in this way keep transmitting these random bit sequences and observing what this means. So observing what's the state of the car, how it changes perhaps every time we send a different packet. In this way, this is how with fuzzing or fuzz testing, this is how Kosher et al., so these were the researchers from the University of Washington and the University of California, San Diego, when in 2008-2009 they published superb work on some of the first examples of experimental attacks against, of practical experimental attacks against normal cars. And they did this they did the research on this by going through all the potential bits and finding which one does what. So which one is the one that disables the engine, which one is the one that locks the individual brakes, and so on. So you do this by going through all of these. So this is called fuzzing. I mentioned that there is an identifier, and this identifier is very important because it is effectively the priority. So this bit here, this part here, and for the second one, this is the identifier for these two. And the lower it is, the higher the priority. The higher it is, the lower the priority. Now, CAN bus has a specific mechanism. It's called a carrier sense multiple access with collision detection and arbitration on message priority. So this kind of approach means that the different ECUs, the different embedded systems on this CAN bus, they listen to this network. They listen to see if there is anyone transmitting on it. If no one is transmitting, then they have the right to transmit. So they can transmit only if it is idle. There is no point transmitting if someone else is already transmitting. If at the same time, though, another node, another ECU, another embedded system starts transmitting at the same time, then out of the two, so here we have an ECU A and an ECU B, so these two at the same time are trying to transmit. They happen to, when they started transmitting there was nothing, so it was, they felt that the bus was idle, but it wasn't really, because they started at the same time. And by starting at the same time, then we check which one is the ECU which one has the message with the lower priority. The one with the lower priority is the one that aborts and then waits. So which one is the one with the lower priority among them? Well, we have the identifier of this one being a bit higher. You see the extra ones here, a bit higher than this one. So high priority means, high identifier means low priority. So ECU A is the one that has the low priority. So ECU A is the one that has to wait. So it is ECU A, the one that aborts and waits, and ECU B, because it has a lower identifier, it is the one that will continue transmitting. So let's use this arbitration mechanism in an exercise now. Assume that there is this kind of simplified CAN system. The real one will have at least 11 bits. I think it's milk and it's 23 bits. But this one has only 3 bits. So the simplified CAN system with only 3 ID bits and 3 nodes, A, B, and C. So these are 3 different ECUs, and these different ECUs, so this is ECU A, ECU B, and ECU C, they are connected on the same network, on the same bus. So this is the bus there, and they have 3 different identifiers, which means they have 3 different priorities. So the one that is the lowest is A, and that has the highest priority. The one that has the highest value is B, so that's the one that's expected to have the low priority. But let's see now in practice how this works. So how does the arbitration look like if the nodes are sending simultaneously? So they will all have, they all think that it is idle at the time that they start, but then by the time they start, they all are transmitting at the same time. So the 2 of them will have to abort. Let's see how they do it. So we have a little table there with the different nodes, node A, B, and C, and their IDs. And let's start transmitting. So bit 1 for A will be a 0. So this here, 0 will be the first bit. And for B, it's a 1, isn't it? So B is 1. And for C, it's a 0. Now, what happens is that out of all these, we do a logical AND. Now, a logical AND means, let me write it somewhere there. It means that, effectively, it means that if it is not a 1 and 1, everything else is a 0. But let's see. So logical AND 0 and logical AND, that is 1 equals 0. If it's 0 and 0, it's a 0. If it's 1 and 0, it's a 0, of course. And if it's 1 and 1, it is a 1. Okay, so anything but a logical AND 1 and 1 will be 0. Everything but that will be 0. So when you have 0, 1, and 0, then there are zeros in there, and zeros clearly, as we see from here, zeros clearly beat 1. So if there is a 0 in there, that beats the 1s. So the bus value, so what will be transmitted on the actual bus will be a 0. Of course, that's expected by the way it works, the way we have set up the CAN bus system with a twisted pair, the way we have decided what is 0 and what is 1. Because 0 means that there is a difference in the voltage, 1 means that there isn't one. So if you keep transmitting ones, basically there's no difference in the voltage. But if you transmit even 1 0, then you have created a difference in the voltage, and that will be seen on the bus. So that's why the bus has a 0 there. And then B has to stop. Why? Because it checks. I was transmitting a 1. I transmitted no difference between the signals, but I got a 0. So between them, there is a difference. So maybe I'm not the only one transmitting. I should stop. So what happens is that B then stops, and then we have A and C continuing. So A, for the next one for A, is a 1, isn't it? So there's a 1 from here, and the same for C. So there's a 1. Now, logical AND 1 and 1 means 1. So we have a bus value of 1 there. Let's do the next one. So they both continue because they see exactly the value that they transmitted. They think they're on their own since what they transmit they see on the bus. So let's see now the next one. So bit 3. Bit 3 will be a 0 for A. So that's a 0 there. And it will be a 1 for C because the third one is a 1. So there is a 0 and a 1. What happens with 0 and 1? Well, we have a 0. 0 and 1 is 0. So we have a 0 on the bus, and as a result, C is the one that says that there is a difference between the bus and its own value. So C realizes that it is not transmitting on its own and that it should stop, and it does. And then A is the one that continues and sends the rest of the message. So in this way, the arbitration mechanism, this is how the arbitration mechanism will work on CAN bus. Let's see now some security aspects now. Since we're talking about cyber-physical security, let's talk about some security aspects related to CAN bus. Now, CAN bus to connect to physically is very easy. You can find CAN bus, the port, what we call the onboard diagnostics port, the OBD, or EOBD in Europe, which is the one where the mechanics would connect their laptops so as to, or their devices, so as to detect if there are any faults on the car. So this is effectively an end of the network of the CAN bus. So when one puts anything there, if anyone connects anything there, let's say a laptop that pretends to be an ECU, for example, then it effectively directly connects to the network. And what it can do from there is that, for example, it can start transmitting frames itself. So let's imagine we have a laptop. It pretends to be a part of the vehicle, a new ECU in a sense, and it starts sending traffic. If it starts sending traffic that has a very low identifier, that means it has a very high priority. So it will be effectively jamming everything else. It will be causing something like a denial of service to everyone else, because everyone else having a higher value for identifier will have lower priority than this rogue node. So they will not be able to transmit at the same time. So the first attack you can do by physically connecting to the vehicle is that you can have a denial of service by this flood of high priority messages. You can also read all the messages that are transmitted on the CAN bus. You can transmit any fake messages. So you have this laptop being configured in such a way that it can transmit information on this network, on this CAN bus. Transmit commands to actuators. So for example, like the researchers did in their fuzzing, when they looked through all the different combinations of bits for the message, for the data of the CAN message, and then send messages to actuators and have the various things happening on the car. Or replay actuation commands. So capture a command as it is traveling through this network and then replay it a bit later at the wrong time. A different type of attack, that's perhaps, well, the first one is is pretty easy if you have physical access. If you don't have physical access, it's extremely difficult, of course. You need to have some kind of device connected to that OBD board, like those insurance boxes, for example, or these telemetry units, so as to have any access remotely to the CAN bus. But without one, you basically have to physically connect to the CAN bus. And you may have noticed that the CAN bus is usually under the dashboard, somewhere under the steering wheel. So it's pretty much the same place for every car. If we are to go now to a scenario where we have a lot greater impact in a completely different scale than the one before, then we need to think of a scenario where where perhaps malware infects some dealerships' laptops, and then the mechanics will be inserting these laptops every time they connect to a car, and through them send malicious traffic, perhaps, or some kind of malicious command to all the vehicles. So effectively, in this way, it's a larger scale disruption scenario where some kind of malware is able to be distributed across different cars through the mechanics. Again, a pretty far-fetched scenario, but I think it's worth mentioning it. And a much more common scenario, much more practical, certainly, is the attacks that target the smart key. Now, the attacks that target the smart key, what they do is that they tend to need two different attackers working together, I mean. So normally the smart key operates by the owner being near the vehicle, let's say 2 meters away from the vehicle, and sending a low frequency signal. Now, this low frequency signal is also a low range signal, and the vehicle, by receiving it, knows that the owner is nearby. So if it is nearby, I will unlock. So that's the logic of the smart key. It unlocks the car automatically by having the owner being near the car. That means, though, that it can be, the way it can be exploited is if this message, this signal coming from the smart key to the car is received from a different distance. So think of the case that we have there, where we have two attackers, and this is actually a paper from 2011. It was shown for the first time in a research paper there. So Francillon, Danev, and Capcom, they are the researchers who did that. They show that you can have two attackers. The one attacker has equipment, is near the owner. So let's say that the owner is going to pay for the ticket or something, for to pay for the parking for the car. So it's a few meters away, and then the one attacker goes near the owner within distance of, let's say, 2 meters, so within low frequency communication distance, and has a piece of radio equipment in the bag. Now, this piece of radio equipment is what it does is that it captures the signal from the smart key that is in the owner's pocket, and then retransmits this signal. It relays it actually over a wireless channel that it has created, that this wireless device has created, and sends this signal to the other attacker, to attacker 1 in the image. So we have the signal being captured from the owner's key, relayed over a different channel to the attacker 1, and then from attacker 1 we have the car thinking now that, well, I can see a signal at a distance of 2 meters. I'm sending this signal and it's received at a distance of 2 meters. So surely the owner must be next to me. So if you see, if we see again now the direction, there is the low frequency signal coming from the car. It is captured by attacker 1. So there it is, attacker 1. And this radio equipment is relaying it to attacker 2. Attacker 2 is next to the real key, within, let's say, 2 meters from the real key. So this is where the real key is. So sends the low frequency signal to the real key, and then the real key is designed to send over UHF, over ultra high frequency communication. It is transmitted to send back to the car the response. So there is a cryptographic operation that is happening there between the two, but it doesn't matter because the key is the legitimate key, and it's the legitimate key that is deceived into thinking that it is near the car. How was that? Why was that? Because there is an assumption, effectively. The car and the key, they trust that if they are within range of each other, then within LF, within low frequency range with each other, then they must be near each other, which is not true if someone has captured the signal and has relayed it over a different, longer distance channel.